Well, first thing, it implied that it came from outside the solar system because gravity cannot bind it to the sun. It was moving too fast for that. And the other thing is that the object was relatively big, possibly tens of kilometers, the size of Manhattan Island. And if that's the case, it was 1,000,000 times more massive than the previous objects from outside the solar system, and that was puzzling.
Two massive celestial objects, Swan, C2025R2 and 3I Atlas, recently made their way into our solar system from the farthest reaches of space, both hurtling toward the sun just weeks apart. What's even more puzzling is that these objects came from completely opposite ends of the sky, creating an unprecedented astronomical anomaly. This rare cosmic event has left scientists and astronomers grappling with questions. Swan was first detected by the SH spacecraft's Swan instrument on September 12, 2025. It was a bright, unmistakable object with a tail stretching nearly 2.5 degrees across the sky, approximately 5 times the width of the full moon, a scale considered unheard of for a newly discovered comet. Its brightness was such that it was visible with small backyard telescopes and binoculars. Just 2 days after the initial satellite alert, an observer in Australia captured a dramatic image of the object, showing a streak of light so long it almost exceeded the camera's field of view. Swan's physical dominance in the inner solar system was compared to events not seen since the days of Hale-Bopp. Adding to the mystery, just days before Swan's astonishing discovery, another object, 3I Atlas, had already been detected and was inbound, making its own approach from a completely different sector of the sky. While Swan's path could be traced back through the constellation Aquarius, Atlas was observed entering from the direction of Sagittarius. On a celestial map, these two arrival vectors were separated by more than a quarter of the celestial sphere. Despite their disparate origins, both objects were set to reach their closest point to the Sun, their perihelion, within the same exceptionally narrowed 10-day window. Swan's perihelion was estimated to occur around October 20th at a solar distance of approximately 150 million kilometers. Atlas's perihelion, just 3 days earlier on October 17th, would see it skim past the Sun at roughly 203 million kilometers. This placed their perihelion points only about 50 million kilometers apart, a distance closer than Mars ever gets to Earth. The geometry of their orbits was striking. Both objects were on steeply inclined paths, with Swan's trajectory tilted more than 60 degrees off the ecliptic, and Atlas's path nearly perpendicular to the plane of the planets. The drastically different approach angles made the probability of both objects crossing the inner solar system almost simultaneously and at such similar solar distances purely by chance, vanishingly small. Astronomers accustomed to the random arrivals of long-period comets and interstellar objects with perihelia spread across months or even years found this near synchrony truly baffling. The precise timing of their approach introduced an additional layer of intrigue and concern. As both Swan and Atlas swept through their closest solar approach, Earth's telescopes were rendered effectively blind. Between October 8th and 18th, the sun's intense glare created a formidable blackout window, making direct observation impossible during a critical period when any unusual behavior from these objects would be most visible. This meant that the moment of closest proximity for both objects, not only to the sun but also to each other, would occur just beyond the reach of ground-based observers, leaving no way to witness these events unfold in real time. The fact that two such objects, from such widely separated origins, would hit perihelion within days of each other and nearly the same solar distance, and all during a period when the sun itself shielded them from view, defied all usual expectations of chance and pointed towards something far more complex. 3I Atlas initially garnered attention not primarily for its brightness, but for its peculiar characteristics that seemed to contravene established rules for comets. Early spectrographs from the Atlas SpecLab group reported an alarming discovery. The object's composition appeared dominated by nickel, with virtually no iron in the mix. This finding ran counter to everything understood about comets, which typically exhibit iron-nickel blends in their vapor. The unexpected nature of this claim led other labs to immediately call for a rechecking of the data, sparking a calibration controversy that spilled onto astronomy forums and triggered a wave of independent reviews. The debate intensified with subsequent measurements, which revealed that instead of the classic water vapor signature, Atlas's coma ejected carbon dioxide at rates 5 times higher than water, with the 4.3 micron CO2 line dominating every spectrum, while H2O barely registered above the noise. Furthermore, the behavior of its tail proved puzzling. Observers tracking Atlas's motion noticed a distinct pattern of 3 accelerations, each spaced about 2 weeks apart and each coinciding with a sharp change in tail color. This suggested the object might have fired a thruster, as these delta-5 pulses were not smooth, like the gradual push from solar heating, but rather came on fast and then faded. If these observed accelerations were genuine, the implied power source within Atlas would need to deliver energy on the order of 10 gigawatts, roughly equivalent to the output of 10 large nuclear plants, a capability far beyond what any known comet nucleus could muster.
Swan, in stark contrast to Atlas, quickly established itself as an object in a league of its own, prompting an entirely new set of questions. Reflectance data indicated that Swan's core reflected light with a sharp metallic signature. Some amateur spectroscopists keenly argued that this signature matched not just nickel, but a nickel-cobalt blend, materials specifically chosen on Earth for their exceptional strength and resistance to corrosion. The term nickel-cobalt hull soon began circulating in online chat rooms and late-night podcasts, fueled by the object's remarkable refusal to break apart or dim as it closed in on the sun. This was followed by reports of an optical anomaly, a persistent silvery halo observed around the nucleus, which shifted in pattern and intensity. To some, this appeared strikingly similar to a plasma envelope, suggesting a form of electromagnetic shield capable of deflecting solar wind and cosmic debris. This distinctive characteristic led to its evocative nickname, Fortress. Unlike Atlas, which was described as drone-like, quick, agile, and efficient, Swan presented as a tank, slow, steady, and seemingly invulnerable. Its already record-breaking tail exhibited pulses of microthrusts that defied simple outgassing models. Photometric analysis further revealed tiny rhythmic changes in the tail's direction, as if the object were making precise course corrections using bursts of plasma. Each pulse manifested as a distinct blip in the brightness curve, and this pattern repeated with a regularity that was difficult to attribute to random surface eruptions. Adding another layer of complexity were its orbital numbers. Swan was determined to be on a path that would take it around the Sun once every 22,554 years. This staggering cycle implies that if this object were indeed engineered, it would have been on a preset course for a period longer than the entire span of human civilization, arriving now at the same time as Atlas in the same solar corridor. These compounding anomalies, from Swan's sheer luminosity and hints of advanced shielding to its possible armored hull and immense energy output, fostered a growing conviction that it was not merely another comet, but the most formidable object to enter the inner solar system in living memory. Whether a fortress, a probe, or something else entirely, Swan's presence unequivocally forced astronomers to reconsider established rules and open the door to theories previously confined to the realm of science fiction. The converging evidence, the precise timing, the striking orbital geometry, and the convenient blackout window further fueled a wave of mission-oriented theories. One possibility suggested a relatively routine operation, such as a scheduled maintenance or refueling run, with the Sun acting as a cosmic pit stop. In this scenario, both objects could be engineered to utilize solar energy or magnetic fields for recharging, data transfer, or even a systems audit. Another theory posited a less peaceful scenario, a close approach serving as an intervention, a rendezvous to recover or neutralize a malfunctioning unit, or perhaps a competition between rival factions vying for a celestial resource. The estimated power levels for Atlas, around 10 gigawatts, and Swan, a staggering 10,000 gigawatts, strongly suggested energy reserves suited for active maneuvering, rather than passive drifting, with the stepwise accelerations, tail modulations, and microthrust pulses fitting a mission profile rather than random outgassing. Furthermore, the audit chain scenario proposed that Oumuamua in 2017, followed by Atlas, and now Swan, could represent escalating responses to Earth's century of radio transmissions, with each new arrival serving as a more complex probe sent to check in, gather data, or potentially escalate contact. In all these frameworks, the Sun was not merely a backdrop, but a crucial power node, a rendezvous point, and a beacon. While the evidence didn't definitively resolve the debate, it raised crucial questions about the object's purpose. A 22,554-year orbit delves into the last ice age, around 20,000 BCE, an epoch marked by glaciers and climatic shifts that influenced early human civilization. These layers left traces in ice cores, hinting at dramatic celestial events. Some researchers linked these layers to periods when bright, long-period comets might have passed through, leaving not only debris but also stories that could have been passed down through generations. The ancient site of Göbekli Tepe in southeastern Turkey, with stone pillars carved with animals and abstract symbols, has been suggested by some theorists to depict celestial paths, potentially even marking the return of objects like Swan. From October 8th to 18th, all major ground-based observatories faced a mandated shutdown, officially termed solar conjunction downtime. However, internal memos from U.S. Space Command and the European Space Agency reportedly directed teams to suspend all radar and high-resolution imaging of Swan and Atlas, and requests for raw data were delayed. Telescope allocation reviewers, speaking anonymously, described explicit orders to avoid public statements about either object until after perihelion. This created a forced silence during a critical period, leaving only independent astronomers and amateur networks to gather information. In response to the blackout orders, Bill Gray, a veteran tracker, mobilized a distributed network of backyard astronomers and small observatories, urging them to keep your scopes on the sky, log every flicker, and share the raw data before it disappears. Groups like the Abero Tracker Collective in Spain and Portugal pooled sensor feeds, and private astronomy groups devised plans to bypass the blackout using radio telescopes and repurposed weather satellites. This grassroots effort became the sole defense against an information vacuum, with the blackout serving as an invitation for anyone with a telescope or radio dish to join the search. When Swan and Atlas re-emerge, the initial signals may come from citizen scientists, as these two anomalous objects entered the inner solar system together, defying statistical odds and raising profound questions that no agency has yet answered.